So the score, what is the score? The score is the V value.
Okay. In Atari, the score, the reward is the score of the video of the game. It can be in other problems. It's not the same, but when you play a video game, what you want is have the highest score. So you can see the reward is literally the score you get. That's just a practical way of having.
But it requires we have a score for each step, right?
Yes, but
Like
that was implemented by the developers of the video game.
Oh,
I mean,
okay. But for other games, like you don't have a score for each step. You only have a score at the end. What could you do?
okay, yeah. I see the question. True. In this case, in Atari games, you have at the bottom left here, you have the reward that the score that is always shown. Okay. So you could say, well, we don't even need to manually implement it. We just have to extract it from the image somehow. Well, in practice, we could do that, but it's work to do, and we don't want to tackle this problem. We want to do reinforcement learning. So really nice things, and you will see that in the practical session. Researchers, they implemented the video games in the gym environment, for those who know what it is. And we will see, and you will see what it is for the rest in the practical session. And basically, they extracted the reward automatically. So the reward is most of the time when you are doing reinforcement learning, either you have an environment where the reward function was done for you, and in this case, in the Atari games, it's done for you. They coded it so that at every state you receive a reward.
Mm-hmm.
Or in more complex scenarios where it's like a custom environment or it's your own problem you are trying to solve, you don't have a reward function, and now you have to do the dirty work of actually coding a complex function that takes into input every parameter of what's happening and compute some reward. But this step is very important because last time, remember, we had a question about what happens when you don't receive a reward. And indeed, if you don't receive a reward, well, you learn nothing or you can get stuck. So this thing is called reward shaping. Intuitively, if you only provide 0 reward all the time because it's just too hard to code this reward function, and if you only give a reward of 1 at the end of the game, if you win, that's very hard because you can see that the agent must first win its first game before receiving its first ever reward, which is very unlikely because at the beginning he's very bad. So it's always better to have what we call a dense reward, indeed, and that is at every time step you have some value. You have a non-zero reward. But still, now in research, we are able to derive some algorithm that works pretty well, even when you have 0 reward, and like only like a binary 1 reward at the end of the episode. But that's a hard problem. That's like a research problem.
Sorry, can I have one question here? It's just out of curiosity. So, like, in general, we should have one reward function, right? But is it possible to have a couple of reward functions? And for example, if and we invoke some of them in case if only some specific action was taken, like we learned this in Q learning that we have exploration and exploitation steps, right? Like when you just randomly choose any action to explore.
Yeah.
And is it possible to create, for example, like if I have 3 different reward functions, but one of them is the main one, and I rely to that reward function when my gamer or a person does some specific action. So like I have some actions with higher priority, But if it's not doing any action, so if those actions are not invoked, I can just call the other reward function, which grants very tiny amount. So instead of having one complex reward function, I have like 3 or 5 or some amount of reward functions, which I can use related to what is the player doing.
Yes, exactly. I mean, this is still, when I meant a complex reward function, what you describe is still a complex reward function. And in practice, you are right. What you are going to do is something that looks like if state is in this list, or if state's properties are like this, then give like that much reward. Else, if those states then give such reward, and else give this reward. And you can say that you have a number of sub reward functions. Like when you code an environment, that's what you do usually. Particular example is, and you could sum those rewards too. You could use the 3 functions at the same time. You could just only use one. Depends on your entirely on your problem. But that's a different work from building the reinforcement learning agents and training it. There's the person. I mean, you can do both. Good for you. But just usually when you are doing reinforcement learning, you assume that, I mean, you have some environment that is given to you like a black box. You don't know anything about it. The model, especially if it's model free. Okay, but of course, like if you have a very particular problem where you have no environment that is given to you because it's just like it's not a common environment. For example, recently DeepMind they managed to solve in simulation the control of a nuclear fusion reactor with deep reinforcement learning. You can easily imagine that you don't find a simulation of a nuclear fusion reactor off the shelf in GitHub. Like you don't find that. They had to implement first actually code the simulation, and then they had to implement their own reward function and everything. And here, that work is especially important because how you define the reward function will impact what is the policy you have at the end. Because your policy wants to maximize the reward. If your reward is ill-defined, or like if you forgot that in some case you should have negative reward instead of positive, for example, well, the algorithm doesn't know that. The reinforcement learning just want to maximize it, so he will maximize whatever you give him. And so the performance can be heavily impacted by how you coded your reward function actually. But that's not. That's more like an engineering problem. Designing the reward function. This course, we assume the reward function is given to us. We can compute the values. We don't think of how it was constructed, okay? But you of course do it yourself. Okay, back to the course. Okay. So we saw that we can approximate value function with deep learning, and we just minimize the mean square and error loss with stochastic gradient descent with a target Q value estimate instead of the true Q value. But the problem is that now that we are in an approximate setting, the theorem we saw last time that says that we converge under those hypotheses doesn't hold anymore. And actually, we can diverge. We have no guarantee that the algorithm will actually converge to the true value and that our policy will converge also. There are multiple causes to these problems. The most important one are correlation between samples and non-stationary of targets. So what is correlation between samples? Is basically remember, when you do Q-learning, you update your table every time you have a new sample, every time you have a new state action reward state tuple. Okay, like you act in the environment, receive new action, reward, and states. You store that, and then you use that to update your Q value directly. That's what Q-learning is. Here we use deep learning and Socratic agent sense to do these updates. And because we do stochastic, maybe we don't want to do like purely stochastic with mini batch size 1. Maybe we want to do mini batch size of 10. So for example, we collect 10 samples and then we update with all those 10 samples. And the thing is that all the samples were collected with the same policy, and also potentially, so they are correlated already. But even more important, potentially they are like following each other, because those samples might come from the same trajectory, just one after the other. And that's a problem, because there was a big assumption in deep learning we did, is that when we do stochastic gradient descent, the batch are uniformly sampled in IID. In here, it's clearly not the case, because if we just takes continually what arrives, what is generated by the agent that interacts with the environment, this is clearly not uniform. This is clearly super correlated, not IID. So deep learning will suffer from that. Also, there's a problem of non-stationary targets. So the targets are the Q-value targets, remember? In Monte Carlo, it's the full return. In TD learning, Q-learning, it's like the one-step bootstrapped value. And well, in deep reinforcement learning, those targets are non-stationary in the sense that the values, those target values, will change over time. Why? Because at the beginning of training, your policy is really bad. So you will receive very little reward. And because you do bootstrapping, well, the target is using the current estimate to compute a new target. And the current estimate is, well, your policy is bad. I estimate that your value is bad. That's just the definition of the value function. The value function estimates a policy. And if the policy is bad, well, the value function is bad, meaning the value will return very low. The value function will return very low values. But then, as learning goes on, as the agent progresses, he gets better and better. And so he reaches states that give it high reward. And now, if the Q-value function is still learning correctly and is approximately good, it will evaluate that some state gives high reward, so high values. And so the outputs of the Q-value function over time will increase. So the targets, because we do bootstrapping, we use the same estimate to compute these targets, to update it, will increase also. And so the targets that you use to fit your main square error loss changes over time. At the beginning, for a certain action, you might have 0, but then at the end, you might have, oh, actually, for the state in action, I didn't realize at the beginning because I was bad, but actually, this state in action, I should put them a high value because they lead to really high reward later on. And this non-stationary is also really bad for deep learning. And a more like deep learning example of this is in the case of continual learning. For example, when you want to do like a image classification, but you don't have access to all the classes at the same time. For example, in the beginning of training, you only have access to like a fraction of all the classes of images. And then when you train, you gradually shift the classes you have access to. And imagine at the end, you don't have access to for example, so at the beginning, you train only dogs, then a mix of dogs and cats, and then at the end, only cats. This is a non-stationary target also. and this will hurt the performance of deep learning. So two solutions for this problem that were brought in the GPU network paper is experience replay and fixed Q targets. Experience replay, the idea I already talked a little bit about it last course, but the idea is really simple. Is that you don't want your sample to be correlated. Well, what do you do? See, every time you collect some experience in the environment, you put it in a big table, a big memory, and you store it forever. Until you have full memory, and then you start emptying it like FIFO, first in first out, for example. And then which samples do you use to update your Q-value functions with the loss you have defined? Well, you sample from this replay buffer like a uniform probability. That way, you ensure that your samples are not correlated anymore because they don't necessarily follow each other, and also they don't come from the same policy. And the replay buffer has a huge impact on performance, really big. So the algorithm looks like it. You sample an experience sample from the dataset with this replay buffer. You compute the target value with this sample, and then you use stochastic judgment to update the network weights. And you can use that with more than one sample because we are in a mini batch stochastic descent. You can use 10 samples and average the loss over it and average the gradients. The same you would do in deep learning. And I didn't do a slide. Okay, fixed Q targets.
Idea of the
sorry,
of these tables.
Sorry, can you repeat it?
So the idea of experience replay is just to shuffle all these tuples.
Yes, to shuffle and reuse. This has two benefits. First, yes, we decorrelate by shuffling because we store and then we sample uniformly with replacements. Okay. So second is reuse because we replace. We don't when we sample, we don't remove it. We still leave it in the memory. We reuse. And why reuse is useful? Because now, instead of using a sample only once to update our Q-value, we can reuse it many times during training, and this will improve significantly the sample efficiency, which is the number of steps in the environment we need to do to converge, which is a really good thing. Basically, you can, for example, sample at every time step 256, like some batch size, 256 samples at every time step, and do one environment step. And this way, for every time step of the environment you do, you update with 256 samples, and you will reuse samples that way, and you will converge much faster. Fixed Q targets. There was the problem of these non-stationary targets. Well, a simple fix that is very simple. Well, you just you make so that it's stationary, at least temporarily. And so what they did is that we will talk about it just after, actually. But you can imagine that, for example, you have a second Q-value network that is a copy that has the same weight, but then you regularly freeze the weight of this one, and you just compute the target with this second network and not the first one. And the weights of this copy are only updated every 1,000 steps. That way, for a length of 1,000 steps, the Q-value is constant, so the targets are constant. And it's like a very practical way of solving this problem, and it works very well in practice. So now we'll explore more deep relations between how you can use the idea of deep learning in reinforcement learning and vice versa, especially deep learning aware reinforcement learning. So how do ideas from the previous lecture apply in this setting? How can we make the algorithm more compatible with deep learning? And how can we make deep learning models more suitable for reinforcement learning? So we know from deep learning that SGD needs samples to be uniform IID, as I said. And it's always better to use a mini batch instead of a single sample for stochastic gradient descent because it's less noisy and you cover faster. You know, a mini batch is the trade-off between using the whole dataset and one sample. Remember the little image. If you want one sample, the optimization is very noisy. And if you use the whole dataset, it's very smooth.
Tom, you are mute. We cannot hear you.
Okay, I was muted. When did it stop?
1 minute before.
When?
2, 3 minutes.
A bunch of images. You mentioned something. Mini batch. I think you mentioned a mini batch.
Okay. Yeah. So, yeah. Okay. It's just this slide. Yeah. So, mini batch is better than a single sample, as we saw, and because it's less noisy. That's basically what I said. Remember in deep learning. The bigger the batch, the less noisy it is, but also the slower. You need a bigger GPU, etc. So as I said, when you are online reinforcement learning algorithm, you do an update every new sample, and those samples are strongly correlated. So the one solution we did was to use experience replay, because they will mix online updates with updates on data samples from past experience, past policies. They correlate and make it more offline through this correlation, and that way we can do mini batch updates. That's what I explained. So if you have a big memory, you can sample multiple samples instead of just waiting for one every time. That's very practical. But there are other ways to address the two problems of correlation and the non-stationary targets. We can derive better online algorithms, which, for example, what is called eligibility traces, basic complex notions, and it's not the scope of this course. You can use just simply better optimizers, momentum, Adam. That might work. You can do planning instead, so turn to model-based reinforcement learning. That's what we will see in the last lecture, and you can change the problem itself. For example, use parallel environments. That's what I mentioned the last time at the board. Remember, if you have problems with samples being highly correlated, and also if you use an on-policy algorithm like SARSA, you want your samples to be on policy. And if there is a slight delay, your samples might be slightly off policy because they come from a slightly older policy. And so if you use many environments in parallel, you might solve both problems at the same time, because you can just do one step in every environment with one policy, which is very fast, and it gives you a lot of samples that are not correlated but still from the same policy, instead of doing n steps with one policy in one environment, which are highly correlated, and potentially you might have changed already the policy while you are doing that. More importantly, in deep reinforcement learning, there is something called the deadly triad. And it's the reason why the Q-value function approximation might diverge when you use deep learning with it. If you combine experience replay with bootstrapping, so we do Q-learning. Bootstrapping means the target, remember, is use the current estimate. So if you combine experience replay, bootstrapping, which means we do Q-learning, and deep neural networks, things can go really south. In practice, it can diverge really badly if you're not careful. And so we might wonder, okay, but is this actually a good idea, what we are doing? Because literally, DeepQ network, this algorithm we just saw, is doing those three things. You have experience replay, so your data is highly off policy. You have deep neural networks, so you have you're doing function approximation, and you're doing bootstrapping because the target is the greedy policy. It's not like SARSA where the target is on policy. Should we actually do it? Well, in practice, it still works, and it still works pretty well. And that's one of the strengths of, I would say, some would say, or some people that are more inclined to pure mathematics would say it's a horror, but all the math and all the theory tells us that it's not supposed to converge, or there is no reason it should converge, or actually it should diverge. I mean, we don't have a proof that it should diverge, but it looks like it's really unstable. But in practice, well, it first diverges usually, and then it converges. So you have what is called a soft divergence. And in practice, even with this deadly triad, deep transformer learning still works and works really well. And that's why it got really popular, because we don't really understand fully why it works so well, even though there is no assumption yet on the convergence. So now they are starting to have some research that have some clues about why it works. But still a hard question, because we don't even know fully why deep neural networks converge to such good solution and can generalize so well. It's like a hard mathematical problem. So if you add reinforcement learning on top of deep learning, well, the problem becomes even harder. But we still have soft divergence. As you can see at the beginning of training, your values are really high. I mean, the errors, so here is plotted the errors during training, is really high, potentially extremely high. And so the value estimate can be quite poor for extended period of time and can hurt optimization. And so an idea to solve this, to help this problem, is to use target network. And that's already what I hinted, is that you use only, instead of only using one neural network, you use two, which are same architecture for the, but one you optimize, and the other one you only use it to compute the target of the Bellman residual error, your loss in the DeepQ network. And so this target network, you hold fixed the parameters to compute the bootstrap targets, and you only update the parameter, for example, periodically every few hundreds or thousands of updates, and you can update then, for example, just copying the parameter of the first network. And this breaks the feedback loop, especially the problem of bootstrapping that makes this soft divergence happens, and it really helps in practice. And so that's why also when you are doing such things, it's important to tune this hyperparameter, which is the period in which you update this target network, because your performance can actually be greatly improved by just tuning this period hyperparameter. So voila, that's how it looks like in pseudocode. That's what is the most interesting to you. Deep Q-learning. So you have a for loop at every state. You sample an action 80 with the epsilon greedy policy, so that you know. You implemented in the last practical session. You observe the reward in the next state, so that means you apply the action to the environment. You saw how to do it also in the practical session. Then you store the transition in the REPL buffer now. So this requires a little bit of code, but it will be greatly simplified for you in the TP. Most of the work is already done for this part. And then you can start doing the updates. So you sample a mini batch of samples. You have, I don't know, n samples. Here we have a loop for every sample in the mini batch, but of course on GPU this runs in parallel, of course, because we are using, for example, PyTorch, and when you optimize the loss function on deep neural networks, you can give the batch of inputs to deep neural networks, and the loss will be batched also and parallelized. So this for loop is more for like to acknowledge that there are multiple samples, and that we compute this for every sample. And so you compute the target with the formula, the Bellman optimality equation, as you see with the max. Just for your information, the first if is, you can see that the target is not the bootstrap target, but just a reward. Why is that? Is because in the case the episode is terminated, you don't expect to receive any reward anymore, because it's the end of the episode. So actually, you shouldn't, to the target, you shouldn't add this gamma max something terms in the target, because in this case, you know for a fact that you will receive 0 rewards after, because it's the end. So the return, the target return should only be R, the reward. That's why you have this dichotomy. And then you have your targets, and you can do the gradient descent step by computing the mean square error loss, like a linear regression. You have your target Y, and you have your predicted action value that is computed with a forward pass of your neural network. And at the end, you see the little condition if modulo TC equals 0. This is, as I explained, to update the weight of the target networks periodically every C steps in this case. And as you can see, we used the weight W minus to compute the targets, and not the weights of the main Q-function network. So it's not that complicated. It looks a lot like Q-learning already, just that now you don't have a table anymore. You have a deep neural network and a REPL buffer and this target network. We can also implement ideas we saw last time, double Q-learning. We can do deep double Q-learning in order to fix the infamous overestimation bias we saw last time. Remember, you can double Q-learning used to keep in memory 2 versions of the table, and you update those 2 tables with a mixture of the first table and the second table, so that you decorrelate. You have some decorrelation, and it solved the overestimation problem. Remember, we did it on the board. Well, in this case, that's super good because we already have a target network. We already have two networks because we wanted to fix the problem of stationarity. So actually, we have nothing to do. We already have two networks. And actually, these target networks allow us to solve both non-stationarity and overestimation. And it has two beneficial effects. And so here you can see that so if you plot the distribution of the outputs of the Q values for some, I don't know, some interaction, some amount of interaction with the environment, on the left you have, it looks like this, and especially you have 61% of the distribution that where the Q value is above 100. And we can imagine, for example, they put the limit 100 here because the environment has at the maximum a length of the episode, a maximum length of 100. And if you have one reward at every step, the maximum reward you can get is 100. So outputting a value of more than 100 makes no sense because it's impossible. Well, with overestimation, actually 61% of the samples they're estimated with more than 100, and a lot of them in even 100,000, which is a really bad thing. So by using the target Q network, we actually reduce these facts a lot to 14% and even 10%. Another idea to improve the performance of this algorithm is to use prioritized replay. Basically, not sample uniformly anymore. And the idea is that the uniform sampling assumption is pretty naive because potentially there are some samples where we can learn much more than others. And it says that you can easily imagine that some samples are more interesting than others. For example, in the case of a robot that wants to grab some objects, okay? At the beginning of training, most experience will look like random noise of the robotic arm, just random noise. It's not super interesting. But then imagine by luck, the robot actually like touch the object and slightly grabs it by just some expression luck. This, we want to learn a lot from this particular sample, and we can learn a lot because this one was the only successful sample from a lot of them. And so the idea is to sample this particular sample way more often than the random, uninteresting random noise movement. And so a basic implementation of this idea is to have a priority associated with every sample in the replay buffer that is computed with the temporal difference error on this transition. So remember the algorithm. The temporal difference error, I mean, it's this one. It looks like this, or it looks like the mean square error here. That is where it's written y minus the Q value prediction. This is the TD, what is called the TD error, temporal difference error. This is the same error that you have in temporal difference learning. And well, this error is indicative of something. It tells us if this error is low, it's because potentially we are already good in the states, which means we already saw a lot of them. So minimizing this error on those states, we are already minimum. We know already we have nothing much to learn anymore. But imagine what happens. What does it mean when you have a high error here? It means we are really wrong about the true Q value of these states. And why are we wrong? Potentially because we didn't see this example before. We never saw this example before, so the Q function network could not output a accurate estimate. And so having a high TD error is a good indicator that we just encountered a new state that we never saw before. And so basically, this prioritized replay technique says we want to sample more often from states that have a high TD error, because it means those are new states and potentially interesting states. So that's the whole idea. But by doing this, you sample states away from the state vegetation under the agent policy, which means you are even more off policy, because now it's not even uniform, and the distribution of your samples doesn't even look like the distribution of your policy. You are like actively changing the shape of the distribution you are sampling with this prioritized replay. And so the updates can be even more off policy, which can hurt even more divergence, as we saw, and hurt the deadly triad even more. So we can correct this off policy problem with importance sampling. That we saw on the second course, if I remember. I'll refer you to this course if you're more interested in that. You can also correct this with multi-step control. Remember, until now we said we do bootstrap prediction with the one-step bootstrap. We can also do n-step, which is instead of only using one reward and then directly using the estimate of the value for the rest, we can say, okay, we collect first n rewards along the trajectory, and then for the rest of the future, we bootstrap. We use the Q-value function, approximation. And so the return is partially on policy, which corrects a little bit the problem. Also, it's less greedy because we are more on policy, but it's still a policy improvement step, so it's a good one. And especially, it might be especially powerful for deep reinforcement learning, multi-step evaluation, because as you can see, by using 10-step bootstrap, you actually completely solve the problem of overestimation over just using one step. So it can, it's another way of reducing the reliance of bootstrapping and breaking the daily triad. Finally, a little talk about architectures that we can use for deep reinforcement learning. In deep learning, we have three main types of architectures right now. I mean, four now, but you have translation invariance invariant networks, CNN, that are used for images. So that, for example, translation invariant means a cat is still a cat no matter where is it in the picture. It is translation invariant. You have networks that have long-term memory with the gating operation, like in LSTM RNN. But even now in transformers, and you have those permutation invariant equivariance networks that are transformers based on attention. And the question is, shouldn't we just copy this architecture that are designed for supervised problem? Well, no. Because the structure, as I said, of the reinforcement learning problem is not the same as simple supervised learning. So the question is, which architecture should we use? And for example, this dwelling architecture is a nice example of a network that is specifically designed for deep reinforcement learning by implementing the inductive biases of RL directly in the network. So we could say, we could decompose actually, that's just the math, the action value function, Q of S and A, is equal, mathematically speaking, to the value function plus the advantage function. We saw that in the first course, but if you don't remember, well, the advantage function basically tells us how much more value do we get by knowing the action we need to perform. So like, it's a way of decorrelating states and action values. So you can see that as, first you estimate just the states, kind of like you do the average of all possible actions. And then the advantage tell you, okay, now how much do we correct the value to take into account the action? And well, the idea here is very simple. Instead of having this Q network at the top, where you have a Q network that outputs Q values actions directly at the end. So like here, it's like looks like a bar because it's actually like a one like a vector, and each value in the little q is a value for each action. And in the bottom, for the intermediate layer, you could actually implement it this way, where you have one layer which outputs only one value for the states, which is basically seen as the value of the states. And then at the bottom, you have the advantage values, and then you sum those two, and it gives you the Q values. And this allows to improve performances in some cases. Okay, there's an image missing, but just to make you imagine, if this is like a driving video game in Atari, and the little orange dots here are what we call the it's which pixel some part of the network pays attention to, kind of like the receptive field of CNN. And on this image, we paint in orange the pixels that are critical for the activations of the top part, the V part in this network. And so the V part is the value of the states. And the value of the states, well, we see that it really looks at pixels that are far ahead. So intuitively, it makes sense. It's like, okay, if we want to evaluate globally the states, we want to look ahead and see where we are going. Kind of. The image is not here, but if you look at the pixels that are activated by the advantage function, those pixels will be really close to the car and just in front of it. Why? Because you might have obstacles appearing last moment in front of the car, and depending on the action you took, the action value will be really different. So you have this way two networks, two like sub-networks, one that looks ahead and just deals with like global general average value of the states by looking ahead. And you have the advantage sub-networks that looks more like at short-term instantaneous obstacles or objects, and look at this to correct the value. I'm almost finished, and then we can have the break and go to the TP. In supervised deep learning, we often find that by increasing the data and the capacity of the network, so like the size of the network, there was a question on that. Oh, question, what does the objective function look like of the dueling network? That's a good question. Exactly the same, because as you can see, if you look at a dueling network at the bottom, the output of the Q function network is the same shape. It's like a vector with one value for each action. It's the same shape, so the loss is the same. The dueling network, what is changed is just in the intermediate layers, you have two streams. Instead of like one layer, you have two parallel layers, and each layer, it's a way of implementing an inductive bias. But if you hide like all the middle parts, well, the input and output look the same. So the loss is the same. Nothing changes. It's the same loss as a mean square loss for Q. Yes.
Like the two branches also branches or like more as right? Like
Sorry,
because you before the last layer you have a V and A, but how could you know one represents V and another one represents A?
You don't enforce it. It's done implicitly. It's done. It's like it's the exact same question as how do you ensure that convolutional networks, the early layers, they encode for low-level details and features like colors and small shapes, and the last layers they encode for like high-level objects like a whole car or something. Like, how do you ensure that you have this hierarchy? You don't. It just appears by itself because you made it that way, because the layers are subsequent, so it will appear like that. Here, it's kind of the same way, is that you structure it this way, and you hope that it will help the optimization, because you have a prior. The prior is, you know that the equation looks like this. You know that you can write the Q function like this, so you could say, okay, let's imagine what do I do if I have two outputs and then I sum those two. Maybe it will help the network actually decorrelate what is important for the state and what is important for the action. And this way, it's like helping it by giving it like a template of how to maybe distribute better the information inside. But you don't enforce it yourself now.
But what if what if I like add three branches before the last layer? Like I can steer a template.
I mean, you could. It won't make sense anymore, mathematically speaking, but it would probably work, to be honest. I mean, I don't know if it will work or not, but
yeah. So it's more like an interpretation by human. Like I guess I assume it would be something.
Yes, but here the difference is that we went the other way. It's like we knew for a fact that the equation could be written like that. So okay, let's maybe implement this prior in the model. Maybe he will not use it at all. Maybe, you know what? Maybe the value will be 0 all the time at this node, and actually it will be redundant. That's a possibility. But also maybe it will actually be helpful during optimization. It's more like helping him, because by doing that, you help the model figure out how the solution should look like. Kinda. Okay, so we saw in deep learning that the deeper the network, the better. Well, in reinforcement learning, it's not that great. And here is plotted the error, the TD error, the loss. And you can see that when you increase the size of the network, the error increases. And so if you use double Q-learning, it fixes the problem, but still the networks are more susceptible to the delay triad. Why? Well, first of all, because you are doing even more function approximation, because your network is bigger, so like the importance of function approximation takes a bigger part. And also, as I said, one possibility is that deeper networks bigger networks have like a more smoother loss landscape. They're more regularized. That's why also in supervised learning, they're generalized better. But in reinforcement learning, that is not necessarily a good thing because the problems might be highly nonlinear and highly non-smooth. And so when you have a smooth loss landscape, you might actually be not able to accurately estimate a Q-value function, which potentially is highly non-smooth. So how to use big networks in deep reinforcement learning is still today a really open question. Like we don't have a definite answer. And like, for example, even me in my research and in my field of research, people mostly use at most like a small ResNet, like ResNet 18, because like using the big networks, like the big vision transformers or like the ResNet 100 or 200, using computer vision is like a no-go because first of all, on the task we are doing, usually we don't need that many parameters. And second of all, it doesn't even work. We are not able to optimize it because it's too big and there are problems. And also, as I said, this deadly triad show that generalization can be tricky. As I said, deep neural networks have a tendency to learn smooth loss function, but the objective and the value function can be highly non-smooth. In this case, for example, where you have a wall, so you cannot go to the other side. Imagine just it's shut off. So imagine imagine if you are on the lower part of this grid. Well, you have some chance to arriving to the goal, so your value will be non-zero. Okay. If you are on the other wall, you have no way to go into the goal, G, so your value will be zero. It is zero by definition in this case, because there is no way you are arriving to the goal ever. But so this is like you can imagine it's highly highly not continuous and non-smooth on the left. And indeed, Monte Carlo prediction, which is unbiased, converges to the accurate view of the value. On the other hand, temporal difference prediction with deep learning, so you have the daily triad, have some leakage problem, where you see that you can already see this idea that the loss function is smooth, and because it's optimizing some sort of like oval at the center, and so it's not able to make this clear distinction. And so those are just ideas of, raw points about the current research. This problem is basically a problem of inappropriate generalization. And many work are trying to solve this problem by learning better representation of the data. And my PhD is on this subject. So the subject is on like representation learning for reinforcement learning, basically. And the idea is to find ways to deduce better representation of the data, better small dimensional vectors from images, for example, that have better properties that makes reinforcement learning converge better, basically. And there are many ideas in this like research direction, but you could share this state representation across many tasks also, and that way enable transfer learning. And you could have, like, for example, predict the value of different policies. So those are like a self-supervised task you could imagine to learn a representation in a non-supervised way without the reinforcement learning objective, and potentially maybe even pre-train this representation. by predicting value of different policies, predicting future observations, predicting or controlling other what is called cumulants, so other predicting rewards from other tasks, stuff like that. And so those are the current research directions in this field. Okay. If you have any questions, I can answer now. And while I'm doing that, I'm uploading the TP on Edunao. And yes, and then I will stay for the rest of the course in this call. If you have any question for the TP or the course.
I have a question.
Yep.
Because in this lecture, you mentioned many times the on policy and off policy. I'm curious, like how it will affect the neural network. Like we should choose a more policy or more off policy. And how to?
I'm not going to lie to you. It depends. There is no better algorithm. I mean, as far as we know, they both have pros and cons. Off policy, the pros of off policy is basically this idea of repair buffer. In deep reinforcement learning, off policy is good when you have a slow environment, and so you need to reuse the data you collect as much as possible because it's slow to. Like for example, even if you are like worst case scenario, you are interacting with the real world. Interacting with the real world is slow. Like you don't get a lot of experience. Like you cannot accelerate the time to have like a million years of experience in seconds. It's not possible. So you want to use at maximum the data that you collect. So off policy is the way because it allows for reuse of the data. On the contrary, if you have a fast environment, okay, possibly in simulation, and possibly even heavily parallelized, so that you can run many trials in parallel very fast. On policy might be better because on policy is designed to take like streaming data that arrives continuously and updates only with this batch that arrives, and then you throw it out, and then new batch you throw it out, new batch you throw it out. And on in practice, on policy is slightly more stable for training a deep reinforcement learning algorithm. So we will see algorithm like that in the next course, like PPO and SAC, that are like algorithm that can handle also continuous actions. And SAC is off policy. It's like SAC is a little bit like deep networks, deep learning for continuous action. And is off policy with replay buffer and everything. PPO is more like SARSA. Meaning that you sample some experience, you use it once, and you throw it out. And in practice, doing that leads to more stable training and less stochasticity and less noise in the training, and might be a better option if you can afford to have a lot of interaction with the environment. But there is no definitive answer. Even in research, like in my research, for example, if I do some robotics, there is no consensus on what is the best reinforcement learning algorithm for robotics. Some people use on policy, some people use off policy. It's unclear.
Okay.
Okay. I was going to say I need to upload the TP. So DTP will be on a DeepQ network. You will implement it. I mean, but it's still very guided, like FTP. A lot of help, a lot of like painful things to implement are already implemented for you, so that you can like focus on the most important and most interesting. And there is two environments: a little fast environment. It's called Cardpole. I'm going to show you what it looks like when I'm finished doing this. Give me 2 seconds. Okay. Tac. Okay. Okay. Tac. So the TPs on the website are also gonna drop it in the chat here for you. Hop là. Okay, I don't know if it's working. Okay. Okay, it's in the chat and it's on the Edunao. So there are two parts and then two like bonus exercise. First on Cardpole environment and second on the Pong video game on Atari. It's more fun. I strongly advise you to run the notebook on Google Colab because you have free GPU. Especially for the Pong video game, because training the Cardpole environment takes a few seconds, so it's very fast. But training on Pong takes millions of iterations, and I measured that on Colab it will take 6 hours. If you want to train it to the end, you don't have to. You don't have to see it start improving, but like for 2 million iteration, it's 6 hours. So depending on how much iteration you want to do. And so yeah, on a laptop, except if you have like a good like a computer at home with a good GPU, it will be slower than that, and you will have to install everything. So it's just easier to make it work on Colab. I made sure all the install they work and everything if you follow the instructions. So it should be good to go. And I will shortly put the I mean in half an hour or in an hour I will put the correction on the now. And And there is no image for the environment card poll. But for those who wonder how it looks like, because otherwise it's just code, it's like, okay, don't even know what we are optimizing. It looks like this. Okay. So this is like the gym website, by the way, which is like a big framework that implements a lot of basic reinforcement learning environments. So Atari video games, Mujuko for like continuous control, some text, like some with so Frozen Lake, remember? Cliff walking, in the example in the course, Taxi, Blackjack, others. Classic controls. Cardpool is one of them, and Cardpool looks like this. You have it's like you have some line. It's like a two-dimensional problem. I mean, one-dimensional in control, and you have some like something that slides on the rail, and you have some pole that balance on top of it, and you need to avoid to make it fall. So like it's like need to balance. I have a pen here, but you guess the idea. You need to balance the thing on the that doesn't fall. It's like a reverse pendulum kinda. So it's a very simple program, but still quite interesting to test reinforcement learning on it. And here, in this case, for cardpool, the states are just positions and angles and velocity of the pole, I guess. No image, so that's why it's very fast. But for Atari, the state will be images, so you need a lot of processing and GPU, and that's why it's slower and it needs way more interactions because the problem is more complex. But by the end of training with the Atari, you should be able to have a policy that works. Okay, I will let you do the TP. I'm coming back in 10 minutes, so I'll just cut my mic. And yeah, if you have any questions, don't hesitate to ask me. Okay, I put the answers to the practical stations on the GNAO. So you have a card pool and DQN that are fully working on Pong also. And I provided some answers to how to do double and dueling DQN. Basically, the answer is quite simple. You just replace some things either in the DQN network or in the learning loop. How to compute the target values. And I let you run that. I didn't run the ablations with double DQN or dueling DQN, but you can do it yourself. All right, so if there is no further questions, I will let you there, and I will see you next week. Bye.
Okay, bye bye. Thank you.